Welcome, fellow curious minds, to another deep dive. Today, we're exploring a really fascinating challenge in mathematics. How do we truly measure agreement, especially when the data isn't just numbers, but qualitative judgments? We're talking about interrater reliability, basically. How consistent are different observers judging the same thing? Think about it. Multiple people, maybe even AI algorithms, classifying identical items, grant proposals, medical diagnoses. How do you really know if their agreement is genuine? Or is it just, aligning by chance? It's not just academic, right? This impacts research, credibility, even the fairness of automated systems. So our mission today, unpack a crucial statistic designed for exactly that, Cohen's Kappa coefficient. We're going to try and cut through the complexity, give you the core insights you need.
It's a fundamental problem, definitely. And it's interesting, the history behind it. While, the idea of a Kappa-like statistic popped up earlier, I think Francis Galton, maybe 1892. But it was really Jacob Cohen who formally introduced Kappa. His 1960 paper in Educational and Psychological Measurement, that really cemented its place in our mathematical toolkit for reliability.
Okay, so let's break it down for everyone listening. What is Cohen's Kappa? Fundamentally, it's a statistic, right, for measuring interrater reliability with qualitative items, categories, not numbers. And its key advantage, why it's used so much in medicine, machine learning, all sorts, is that it's seen as more robust than just simple percent agreement.
Exactly, because it smartly factors in the possibility that agreement could just happen by chance.
Right.
Conceptually, you've got Cohen's Kappa measuring agreement in between two raters. They're each classifying, say, n items into c mutually exclusive categories. The formula itself has two key parts. PO, that's your relative observed agreement, what you actually see, and then P, the hypothetical probability of them agreeing just by chance. So think of Kappa, the Greek letter, like this. If key is 1, perfect agreement. Complete. If con is 0, well, any agreement you see is basically just what you'd expect randomly. And interestingly, it can even be negative.
Negative? What does that mean?
It suggests, surprisingly, that the raters are actually disagreeing more than you'd expect by chance. Systematically, perhaps?
Huh. Okay, that makes conceptual sense. But I can hear people thinking, why not just use percentage agreement? It sounds easier.
No.
It's a real payoff for calculating this P, this chance agreement.
That's the core insight of Kappa. Simple percentage agreement can really fool you. Imagine two people who are terrible at darts, just awful. If they both happen to hit the bullseye once in a blue moon, their percentage agreement on hitting the bullseye might look okay. But it's just luck, right? P accounts for that baseline luck. Kappa forces you to ask, is this agreement actually meaningful, or is it just noise, statistical noise?
Got it. This is where an example helps, I think. Let's use that grant proposal one. Okay, so 2 readers evaluate 50 grant proposals, just yes or no. Simple. Let's say they agreed on 35 out of the 50. So our observed agreement, PO, is 35 divided by 50. That's 0.7.
Right, 70% observed agreement.
Now for P, the chance agreement, we need to look at each reader's habits. Say reader A says yes 50% of the time overall, and reader B says yes 60% of the time. There's a certain probability they both say yes just by chance based on those rates, and also both say no. You calculate those chances for yes, yes, and no, no agreement based on their independent rates and add them up. And for this example, let's say that overall chance agreement, PA, works out to 0.5.
Okay.
So now we plug it in. Kappa equals 0.7 minus 0.5 divided by 1 minus 0.5, which gives us the 0.4.
And that raises the big question. What does 0.4 mean? Is that good, bad, mediocre? There are guidelines out there, sure. Landis and Koch, for instance, have categories like moderate, substantial. But, and this is crucial, these are really just rules of thumb. They're subjective, not hard and fast mathematical laws. Plus, the Kappa value itself can be influenced by things like, well, how common the categories are. If almost everything is no, for example. Or if there's a bias, one rater tending to say yes much more than the other. Context matters.
Which brings us neatly to the limitations. And there are definitely points of discussion here. One key critique focuses on that baseline, the pay. It assumes random allocation given the marginal totals.
Meaning given how many times each rater said yes or no overall.
Right. And some argue this can be misleading. It might mask the difference between quantity disagreement.
Like they just use the categories different amount.
Versus allocation disagreement.
Where they actually disagree on which specific items go where.
Exactly. And Kappa can sometimes be seen as maybe overly conservative, especially if some categories are really rare. It can even be unreliable or mathematically undefined in certain edge cases.
That's all true. And it's why it's good to know Kappa isn't alone. It's part of a family of these kinds of statistics in mathematical reliability analysis. If you have more than 2 raters, for instance, you might look at Fleiss's Kappa, though technically that's a generalization of Scott's pi, not Cohen's Kappa, but similar idea. And there's weighted Kappa, too. Really useful when your categories are ordered, like poor, fair, good. It lets you say some disagreements are worse than others. Shows how we're always refining these measurement tools.
So wrapping this up, what's the key takeaway for you, the listener? Cohen's Kappa is definitely a powerful tool. Its main strength is moving beyond simple percentages to account for chance agreement. But like any statistic, its real value comes when you understand its assumptions, how it works conceptually, and importantly, its limits. It's not a magic number, but it's a robust, often essential part of the toolkit for handling qualitative data mathematically.
Absolutely. So perhaps the thought to leave you with is this. The next time you see a statistic about agreement, maybe in medical research, maybe coding text data, even in machine learning model comparisons, pause and ask, is this genuine consensus? Or how much might just be down to random chance given how the ratings happened? It raises that deeper question, really. How precisely can we ever capture complex human judgments or even machine classifications within this sort of elegant simplicity of a single number?